So now we are ready to look at our first quantum circuit. So how does a quantum circuit work? A quantum circuit consists of wires and gates. It's just like a classical circuit, except that the gates are now quantum gates, and the wires carry qubits of information. Okay. The one other property of quantum circuits is every gate has the same number of wires leaving it as the number that enter it. Okay, so let's make up a circuit which consists of two gates, the Hadamard gate and the CNOT gate. So remember what the Hadamard gate does. What it does is h of 0 equal to plus and h of 1 equal to minus. In fact, h of plus is 0 and h of minus is 1 as well. So it swaps 0 and plus, swaps 1 and minus. So it's a 1 qubit gate. Okay, so now what we want to understand is what's the behavior of this simple quantum circuit, where you first perform a Hadamard on the first qubit and then you perform a CNOT with the first qubit as the source, as the control bit, and the second qubit as a target bit. So let's try to understand what happens if the input bits are both 0. So let's follow the state as we go along. So initially the state is 0, 0. But then what happens after this first Hadamard? Well, the first qubit now is in the state 1 over square root 2 0 plus 1 over square root 2 1, and the second qubit is still in the state 0. So the state here is 1 over square root 2 0 0 plus 1 over square root 2 1 0. Okay, so now this is the input state to the CNOT gate. So what happens after we go through this CNOT gate? Well, okay, so we want to understand what the state is here. What does the CNOT gate do to 0, 0? Well, the control bit is 0, so you end up in 1 over square root 2 0 0. What about 1 0? Well, now the control bit is 1, and so the target bit gets flipped. So you end up in the state 1 over square root 2 1 1. I hope you recognize this state. This is our Bell state. Okay, so here's a circuit that starts with 2 qubits initially in the 0 state, and what it does is it entangles them into a Bell state. Okay, now here's the interesting thing. If you play with this circuit, you'll realize that as you change the inputs from 0 0 to the other three possibilities, 0 1, 1 0, and 1 1, the output state changes between this, what's called this phi plus state, which was what we were calling the Bell state. But in fact, there's a whole basis of Bell states. There are 4 orthogonal Bell states. These are called the Bell basis states. And they look like this. They come in pairs. There's phi plus and phi minus. Phi plus is 0 0 plus 1 1. Phi minus is 0 0 minus 1 1. Of course, with this normalization 1 over square root 2. And then you have psi plus and psi minus, which are 0 1 plus 1 0 and 0 1 minus 1 0. Okay, so you should check that these are 4 mutually orthogonal basis states. They are mutually orthogonal unit vectors. And you should also check that as you change the input bits, say from 0 0 to, shall we do one more example? Let's say, what happens if you start with 1 0? Okay, so suppose that you start with 1 0. Now what's the output look like? Well, so at this point we'll be in the state 1 over square root 2 0 minus 1 over square root 2 1 0, which is 1 over square root 2, 0, 0, minus 1 over square root 2, 1, 0. And now when we feed this through this CNOT gate, and we're looking at the state here, the first part goes to just 0, 0. The second part, the control bit is 1, so we get 1, 1, which is exactly this one. Okay? So check that you understand what happens in the case you have 0, 1 and then 1, 1 as the inputs. Okay, so now let's look at one other aspect of this. Remember that we said the CNOT is its own inverse, Hadamard is its own inverse. So now let's think about it this way. Let's think of the input bits as coming in from this side and the output bits coming out on the left here. Okay, so instead of the circuit being one where you first do a Hadamard on the first qubit and then do a CNOT, what if you first did the CNOT and then the Hadamard? Okay, so just for convenience, let me think of the circuit as running from right to left. Okay, but remember, we could have done exactly the same thing where we flipped the circuit around. So we put the CNOT first on the left, then the Hadamard, and then we put the inputs on the left and the output on the right. It's all the same thing. But for definiteness, what I'm going to do is I'm going to now think of the input as coming in from the right, and I'll keep the circuit the way it was, except I think of the bits as moving from right to left. Okay, so what happens? So let's say that we feed in the Bell state 0, 0 plus 1, 1. We want to know what's the output going to be. What happens? What would the state be out here? Well, I claim it's exactly what it was. So when we started from 0, 0 and we ran the circuit forward, the state out here was 1 over square root 2, 0, 0 plus 1 over square root 2, 1, 0. And then when we ran this forward, this state got transformed into the Bell state after going through the CNOT. Well, what happens if we apply a CNOT again to this state? I claim we come back to where we started from, because you apply the CNOT twice, you come back to where you started from. Okay, so when we move from right to left here, we are just retracing our path. Same holds for the Hadamard. When we apply a Hadamard to this state, we retrace our path and we come back to 0, 0. Okay, so here's the picture you should have. If you start with the state 0, 0, you apply this circuit to it, it entangles the qubits and creates this Bell state. If you start from 1, 0, it entangles it and creates this other Bell state, phi minus. And similarly for 0, 1, 1, 1, it creates these two states. But now you can also run the circuit backwards from right to left. And now if you feed in a Bell state on this side, on the right side, what the circuit does for you as you run it from right to left is it analyzes the Bell state for you and outputs 0, 0, 0, 1, etc., which tells you which Bell state it was. Okay, what does this mean? So suppose that I were to tell you, I have these two qubits. They are in one of the 4 Bell states. One of these 4 Bell states, psi plus, phi plus, psi minus, phi minus. But I don't know which one. Can you please help me figure out which one it's in? This is what you would do. You would create this circuit. Well, you'd create it, to look like this. It first does a CNOT and then does a Hadamard. And now what this circuit does for you is it analyzes Bell states. What that means is, after you run the circuit, if you just measure these two qubits in the standard basis, If you get as output 0, 0, you know that the bell state was phi plus. It was 0, 0 plus 1, 1. If you get 1, 0, you know it was phi minus 0, 0 minus 1, 1, etc. So this is what's called a bell basis measurement. Okay.